Maybe I should get started or wait a little bit. What do you think? Start. Okay, very good. So here I have summarized yesterday's lecture. This is the general form of a system of conservation laws. So I have indicated here the size of the various quantities. Remember that G that is defined on Rn and takes values on the space of n by k matrices is a given, there's a smooth function, at least differentiable. U, which is the unknown here, is a function of the variable x that takes values in Rk. So this is a system of n differential equations in n unknowns. And here I have indicated the notion of the companion balance law induced by functions q, if they exist, that satisfy this equation here for all alphas, where b is some function taking values in Rn. And the question is, what can one say about the divergence of q when u is a function of x, satisfying this differential equation here? And the answer is, if u is a smooth solution of this differential equation, a C1 solution, then the divergence of q of u is 0 because of the definition of q. On the other hand, if u is just a weak solution, we can say nothing in general about the values of this divergence, but as we shall see as we go along, there are good reasons to postulate that the only good weak solutions of this system here, or the only good solutions, are those for which the divergence of this has a definite sign, let's say is less equal than 0, in which case the divergence is equal to some measure, and this is the balance law, a balance law. I also introduced the notion of fronts, and in particular strong fronts. You remember a strong front is a solution of this equation, a weak solution, with the property that it is a smooth function, except across a certain manifold here of codimension 1, in other words, a k minus 1 dimensional manifold embedded in space, with the property that if one considers one-sided limits on either side of that manifold here, then the jump of G applied to n has to be 0. This guarantees that we are dealing with a weak solution of this system here. And again, the question is, what can one say about this quantity here? And this quantity in general is not 0, of course, but if you require that the divergence of q is less equal than 0, then this quantity also takes a specific sign. In fact, it turns out that it will be greater or equal than 0, right? So this is more or less what I discussed last time. And today, I want to consider the special case of systems of conservation laws that are hyperbolic. So I want to introduce the notion of hyperbolicity. Now, if a system of balance law is hyperbolic, it has, first of all, a preferred direction. And for definiteness, I will consider as preferred direction the last coordinate direction. So what I'll do, I will take the point x, which, as you remember, takes values in Rk, and write it as xt, where now x takes values in Rm, and by m I will denote k minus 1 from now on, and t, of course, takes values in R. And I will visualize x as the spatial variable, and t as the time variable, because in the applications, this is the physical meaning of this preferred directions. Okay? And I will change slightly the notation that I had over here. So I will take the last component of G, gk of U, and call it something else, denoted, let's say, by capital H. And I will retain the other components, but now alpha will run only between 1 and 10. Also, the partial derivative with respect to capital Xk, I will denote by this symbol here, and the partial derivative with respect to capital X alpha, alpha running between 1 and 10, I will denote it like this. So this will be partial derivative with respect to t, and this will denote partial derivative with respect to x alpha, alpha going from 1 to m. So now with this notation, this system here will take the form where now the divergence is with respect to the spatial variables only. Okay? So this is the class of systems that I will consider now. And of course you may question why I bother to introduce all this notation last time and waste your time. The reason is that I wanted to emphasize that conservation laws and balance laws arise not only within the hyperbolic framework, in which you do have indeed a spatial and time distinction of variables, but in all sorts of situations, right? So I wanted you to know that this is the natural way of considering conservation laws or balance laws. And now I will specialize from now on to the case of hyperbolic balance laws. So now I want to define exactly what hyperbolic system of conservation laws is. You say that this system here is hyperbolic. If the following two conditions are satisfied, first of all, the differential of this function h is a diffeomorphism, is non-singular. So h is a diffeomorphism. This is an n by n matrix value function, right? It's non-singular. And second, the eigenvalue problem let me write it in components form. Perhaps it will be more transparent to you. This eigenvalue problem, for every new unit vector has real eigenvalues which I will denote like this. Not necessarily distinct, and an associated system of n linearly independent eigenvectors. Now, certain remarks here. First of all, if you recall from last time that variety that I had introduced in order to understand the various classes, the nature of balance laws. Now, in this case, the definition itself will tell me that that variety consists exactly of the following pairs. Pairs of vectors nu minus lambda I, comma, Ri. Okay? So you remember this variety was the variety, I think I denoted it like that, was the set of n v that's how it was defined here, if you remember, with some property. I will not rewrite it here. So this variety here consists exactly these pairs of vectors and vectors in Rn here, right? And you can see that it's quite rich, right? So hyperbolic problems are exactly the problem for which this variety here is very, very rich, right? This is the definition essentially of hyperbolic problems. Now, let me go back to this thing here and transplant these notions here in the new notation. So in the new notation, let me start first, for instance, with fronts. Now, when you have a front, you remember a front was a manifold of dimension k minus 1 embedded in Rk. Now, once we consider Rk as Rm cross R, a stationary surface of codimension 1 embedded in Rk is equivalent, can be visualized as a family of m-dimensional surfaces moving in space-time, right? And in that case, it's convenient to take the normal n and write it as nu minus s. Of course, this is not necessarily nu is a normal vector in Rm. Of course, this is unit vector. This is no longer a unit vector. So here, perhaps I should denote it like that. And in that case, you see that you can visualize this stationary front as a family of m-1 dimensional fronts that are moving in the direction n, nu, with speed s, right? This is another equivalent way of saying this thing here. And this condition here can be now rewritten in the following form. The jump of g times nu is equal to s times the jump of h of u. So this is the first remark. Another remark that I want to make is the following. Since I'm assuming that this Jacobian matrix is non-singular, so locally at least, I can invert the transformation from u to h. I can visualize, at least locally, h as the new state vector, in which case I can rewrite my system in the following form. Of course, I will call this h u again, so I can rewrite my system in the form In this form I would consider as canonical. So from now on I will be writing my hyperbolic systems in this form. Let me emphasize that systems as they arise in the applications in physics are not necessarily in canonical form. They are in this form here. They can be, at least locally, transformed into a canonical form here, but it's not advisable to do that necessarily. Usually, it is more convenient and more instructive to look at the system in their original form as they arise here in physics. But for simplicity, for the purposes of these lectures here, I will be considering only systems that are in canonical form, right? So this is something, okay? Now, another thing I want to do is to transplant this notion of a companion balance law to the new formulation here. So I will take Q and again take Q K of U and denote it by a special symbol here and give it a special name called entropy. And the remaining K minus 1, namely M components of Q, visualized now as a vector U, and call this the entropy flux associated with the entropy eta. Okay. So now if I want to write this equation here, assuming my system is in canonical form, if I write this for alpha equals k, now for alpha equals k, this is now the identity matrix. So you see that what I call here B of U is exactly the gradient of eta, right? So this equation here takes the form where alpha now runs from 1 to m. So instead of saying that my system is endowed with a companion balance law induced by Q, I will say that my system is endowed with an entropy which is associated with an entropy flux Q, and the entropy flux is related to the entropy through this equation here, right? Now if you count equations here, because suppose that I say, okay, I'm giving you a system, are there any entropy flux pairs, non-trivial entropy flux pairs associated with this system here? You see that in this system here we have many equations and we only have two unknowns, namely eta and q. Perhaps you can see that better if I eliminate q from this equation here and find the integrability condition on eta. So if I take the derivative with the gradient of this, you get that eta satisfies the following condition. That this is symmetric. So a necessary and sufficient condition for a function eta to be an entropy, namely to be associated with an entropy flux so that these conditions are satisfied, is this integrability condition. And now it's very easy to count the number of equations here. For each fixed alpha, this expresses the symmetry of an n by n matrix. So there are 1/2 n times n minus 1 conditions for each alpha, and since alpha takes m values, so there are so many conditions that has to be satisfied by a scalar function eta. So we have so many equations and just one unknown, right? Now, you see there is a special situation in which we always have entropy flux pairs, and as a matter of fact, we have infinitely many, and this is the case where n equals 1. If we have a scalar equation rather than a system of equations, in that case, you have no condition here. You can start with any function eta and interpret it as an entropy, and then find the corresponding entropy flux from here, right? But you know, if n is bigger than 1, and especially if m is also bigger than 1, certainly the number of conditions far exceeds unity, and therefore, if you take a random hyperbolic system, it won't have any entropy flux pair, right? Now, it so happens, however, that all systems that arise in the applications are endowed with some special entropy flux pair that is there for physical reasons. Usually it expresses the second law of thermodynamics. We shall see the examples in a few minutes, right? And therefore, we may assume, we may expect that we do have an entropy. And in fact, as we will see today, but even more in the future, it is very important if our system is endowed with an entropy, which is a convex function. And by convex, I mean strongly convex. In other words, its Hessian matrix is positive definite. Okay. All right. So we will see this soon. Its relevance. So I haven't done anything new today, except I have taken what I did yesterday, and I have presented them in the new notation and so on. Okay, now, perhaps I should also say that in this form, the jump conditions have a special name. They are called the Rankine-Hugoniot jump conditions. Historically, this is not necessarily accurate. Since you have the book now, you may read the section, the chapter on the history of the early development of the subject, and then you will see that the first mathematician who discovered the presence of such conditions was Stokes, right? But in any case, Rankine and Hugoniot wrote the correct conditions for the Euler equations. We shall see the Euler equation shortly, and that's why they were adopted as names for these very important conditions. You will see these play a very important role in the theory. Okay. Okay. Now, I want to give you examples of hyperbolic systems, and since you have the book, in chapter 3 you will see a very large collection of examples from all parts of physics, from mechanics, thermodynamics, electromagnetism, and so on. Here I will only consider 2 examples or 3 examples because I want to use them as models for future developments. Right? And the first example is the case of a scalar conservation law. In other words, the case where n equals 1. When n equals 1, you can write the conservation law in this form if you wish. So u is scalar valued. And now it's very easy to see that in that case, this is hyperbolic, no matter what this function g is, this condition is trivially satisfied, the condition of hyperbolicity. And as I said before, in that case, we have no condition here. You can take any function as an entropy. In particular, you can take any convex function. If you like convex entropies, you can take any convex function, interpret it as an entropy, and this is what makes the theory of scalar equations particularly simple. Right? Not trivial at all. It's something that took a lot of effort to develop, but for that case, we have a complete theory here. Now, passing to the case of systems, I want to start first with the Euler equations. Now, what are the Euler equations? Let me write them first here. The Euler equations for the isentropic flow of an elastic fluid, a gas. Take this form here. Let me write things in the form that is probably familiar to you. So the first equation expresses the conservation of mass. Rho is the mass density. V is the velocity. The second equation expresses the conservation of linear momentum. P of rho, P is the pressure that is assumed to be a given function of the density rho. Right. Now, in order to bring this system to my notation here, and in particular to write it in canonical form, I will take rho v, the momentum, and call it m, and then rewrite the system in the following form. And also I have to put here transpose, because you remember my convention is that divergence operator acts on row vector value functions.
Maybe this m times np is the one that replaces.
Right, so it's m, a tensor product m. If m are interpreted as matrices, right? So this is an n by 1 matrix, and this is a 1 by n matrix. So m transpose is the same as the tensor product, right? So this is the notation that I have adopted. It's equivalent to the standard one. Now, for this system, I told you that all systems that come from physics are equipped with a natural entropy flux pair. And for this system here, the natural entropy function is, in this form, is rho epsilon of rho plus 1/2 rho v squared. So you can rewrite it, of course, in terms of the variables rho and m. So I can rewrite this as rho epsilon of rho plus 1/2 rho m squared, okay? Where epsilon, which is the internal energy, is related to the function p as the integral here of let's say P of xi divided by xi squared dxi. So it is the antiderivative, the primitive of this function here. And the associated entropy flux here, Q, is rho epsilon rho plus 1 over 2 rho m squared plus P of rho times 1 over rho times m transpose. Okay, so this is Q. And always addressed to the younger student here as an interesting calculation, show that if rho and m are smooth functions satisfying the system here, then these same functions satisfy the additional conservation law, partial derivative with respect to t of eta plus the divergence of this function here q is equal to 0. For smooth motions, for smooth flows, this equation here expresses the conservation of mechanical energy. Right? Mechanical energy is conserved by smooth motions, smooth flows of that elastic gas. Or I should say that this system here is hyperbolic if and only if the function P of rho is strictly increasing. And again, as a simple exercise for the young people here, show that this condition is exactly equivalent to the statement that the entropy function eta that I introduced here as a function of rho and m is convex. So as I said, it's useful, as you will see, to be dealing with convex entropies, and in that case, we do have an entropy, and we are blessed with the fact that that entropy turns out to be convex whenever the system is hyperbolic. Of course, this condition, which says that the pressure increases with density as you're compressing the body, the density increases, is a very natural physical assumption. Okay? The third example that I will consider is isentropic thermoelasticity. I will explain what is the physical origin of that system, but let me write it first. So in that system, the state vector u is pair of f and v, where f is an n by n matrix valued function, and v takes values in Rn. So we have n squared plus n components, I should say m cross m, I'm sorry. M is the dimension of the physical space. So U is an m squared plus m. So what I call n is m squared plus m here. So you see in 3 dimensions, for instance, this is a 12 dimensional size vector. And of course, the reason that you have to deal with such large vectors here has frightened mathematicians, and for good reasons. Okay? So what are the equations? I will write them in components form because it is more transparent, more efficient. Is that the partial of Fi alpha minus the partial derivative of Vi is equal to 0, where I and alpha run here from 1 to m. And the partial derivative of Vi minus the derivative, the sum of is also 0, where I here runs from 1 to m. So you see we have exactly n equations. Now, what is the physical meaning of this equation here? First of all, what is thermoelasticity? Well, it is the branch of mechanics that studies the deformation, the motion of elastic materials of any kind. Okay. This first equation here, F is called the deformation gradient. And V denotes the velocity. This function here, S, which is m by n valued, and it's a function of F, which is also m by m matrix valued, is called the Piola-Kirchhoff stress. And it has this form. It's the partial derivative of some scalar value function of f with respect to f. So the I alpha component is the partial derivative of the scalar function of f with respect to the I alpha component of f. This function epsilon of f is called the strain energy function. So this equation, the second equation, also expresses the balance of linear momentum, in the motion of any elastic body. And the first equation is just geometric compatibility between the deformation gradient and the velocity. I will not tell you how these are defined. You can find this in the book if you're interested. But this is the form of the system. Let me point out that the Euler equations is a special case of this system of equations here. But of course, these equations look very different from this system here. The reason they look so differently is that these equations are written in what is called in mechanics the Lagrangian formulation, whereas the Euler equations I wrote here in the so-called Eulerian formulation. And if you care, you can see in the book how these are defined, how they are related. So this is why these equations look very different from these equations here. But this equation contains, this system here contains the system over there when this S has a special form that I'm not going to discuss. Let me say that this system here is also equipped with a natural entropy flux pair, and the entropy in this case is the following function, is the function epsilon of f, this function here, plus 1/2 v squared. The associated entropy flux, let's say the alpha component of the entropy flux, is And again, as an exercise, in this case, it's very, very simple. Young students can show that whenever f, v are C1 functions satisfying the system here, then the same function satisfies the additional conservation law, partial derivative of eta plus the divergence of q is equal to 0. Yeah. So indeed, this is, again, an entropy-entropy flux pair. All right. Now, I want to make the following remarks. First of all, when is this system here hyperbolic? It is hyperbolic if this function epsilon here, you see everything that physics provides to the system beyond its form is that function epsilon of f. Once this function epsilon of f is given, you can find S, and therefore you can find your system and you can do whatever you want with it. So hyperbolicity is a condition on the strain energy function, on this function here. And the system is hyperbolic, again, simple calculation, if the following condition is satisfied. If this is positive, the summation here runs over all I, j, alpha, and beta. If this number is positive, for all unit vectors, xi and nu. Okay. All right, I will give a name to this condition in a minute, but let me check. Here I said that the system, in the case of the Euler equations, the system is hyperbolic if and only if the entropy is a convex function. Right? So the question is this also true for the case of this system here? When is the entropy eta convex? So eta will be convex. Eta, you remember, is a function of f and v. And it's the sum of a function of f and the sum of a function of v. This part is patently convex. So this will be convex if and only if epsilon of f, this function here, is convex. So as mathematicians, we would love to get information from the physicists who work with that systems that this function epsilon of f is convex. Right? Unfortunately, that function is never convex physically. And the reason it's never convex, there are many reasons why it's not convex, but one of the reasons why this function cannot be convex is that this function has to be invariant under rotations. In other words, this function epsilon must satisfy this condition. For all orthogonal matrices O here. And it's an easy exercise to see that any function that has that invariance property here cannot be convex. Right? So here we have a very important system in physics. It is equipped with an entropy flux pair. However, that entropy is not convex, cannot be convex. So as you will see, we'll have to pay a price when we try to study this system here analytically. Right? Now, one looks at this condition and asks two things. First of all, doesn't that mean that the function epsilon is convex? Not quite, right? Convexity of epsilon would have meant that we have this type of hypothesis, this type of condition. So this is convexity, right? For all matrices, non-zero matrices, capital V, right? That's convexity. Now you see that this convexity here, this condition here is exactly that one, but not for every V, but only for V's that are of special form. V that are tensor products of two vectors, Xi and Nu, right? And this is exactly the class of matrices whose rank is 1. This is why this condition here is called rank 1 convexity. Now, the second question is, okay, this condition here and perhaps other restrictions imposed by physics tell us that this function here can never be convex. How about rank 1 convex? Can it be rank 1 convex without violating some physical principle? And the answer is yes. So this condition here is physically admissible, and therefore it is natural to assume that this system is hyperbolic, but we should keep in mind that the natural entropy associated with that system here is not convex, and therefore all the theorems that will state, prove, and so on, for the case where the system is endowed with a convex entropy, do not apply to that particular system. You have to consider that system separately. Okay? And you will see how. Okay, now that we have the examples, let me state the Cauchy problem, which is a natural problem that one has to consider for the case of hyperbolic problems. So going back to the general theory here, I assume that I have a hyperbolic system, and as I said before, I will assume that it is in canonical form. So this is the system here. And I will not to state the Cauchy problem for this system. And I'm sure that everybody knows what the Cauchy problem is in general. In that particular case, it means the following thing. I have to find u of xt, where x is in Rm and t, let's say, is positive, with the property that it satisfies the differential equation let's say for x in Rm and t on some time interval, let's say 0t, something like that, together with the initial condition, u of x0 is u0 of x for x in Rm, where u0 is a given function for x in Rm, taking values, of course, in Rn. So this is the Cauchy problem. And of course, the first question is, for what kind of functions u should I try to find a solution? Of course, the first reaction, once you see a system of first order like this one, is to say, okay, u of xt should be C1. Right? So this is a natural definition, a natural class in which one would try to find a solution. Okay? And we shall see to what extent we can do that, to what extent we can find solutions of systems like that that are smooth functions. I will call such a solution in that class a classical solution. So this would be a classical solution, a solution that satisfies the equation for every x and every t in this set. Now, I want to give you examples that demonstrate that when we are dealing with nonlinear hyperbolic systems of conservation laws, then expecting to have a classical solution, at least expecting to have a classical solution for all t, for capital T infinity, is too much. Okay? And I'm sure you have seen this phenomenon that I'm going to demonstrate now, but I want to repeat it, even though I'm sure that most of you have seen this before, because I want to make some remarks here to motivate what I will do next. And you can see the phenomenon that even though one starts from very smooth initial data, you don't expect to have globally defined smooth solutions, even in the context of the simplest possible equation in that class, which is the famous Berger's equation. So from Berger's equation, both m and n is equal to 1. We have a scalar equation in just one space dimension, and the equation itself is extremely simple. Okay, so let me consider, let's say, the Cauchy problem for this equation. Here I want to find solutions for x in R here, and t positive, given initial condition, u of x0 is a given function u0 of x for x in R. And let me assume that this function here is analytic, or C infinity, as smooth as you wish, okay? Let's say C infinity. Okay, now, I'm sure everybody has seen this, but the reason that I'm doing it here is because I want to make some comments. You solve this problem explicitly by the method of characteristic, right? So assuming that you have a solution u of xt, you associate with it curves dx by dt equals u of xt. These are the characteristics associated with the solution u, assuming that you do have such a solution. And you introduce this notation. Over dot means directional derivative in the direction of u. In other words, this will be the partial derivative with respect to t plus u times the partial derivative with respect to x. So in this notation, you see that the equation here tells me u, I assume, is a smooth solution, as I said before, is that u dot is equal to 0. So this will tell me that u is constant along characteristics. But if u is constant along characteristics, then the characteristics are straight lines, right? So for this problem here, what you do is from every point x here, you find the value of the initial data at that point. You consider the straight line whose slope is the value of the initial data at this point here, and you know that along this straight line, u is constant equal to this initial value here. So this is okay. But then one makes the following observation. Suppose that I want to see how the first derivative with respect to x of that solution propagates along a characteristic. So I take the first derivative with respect to x, call it v, differentiate the equation with respect to x, and I notice that then v satisfies along the characteristic, using this notation here, the ordinary differential equation v dot plus v square is equal to 0. Right? So this tells us right away that if you have initial data for which, even at one point, the x derivative becomes negative, then the solution has to blow up in a finite time, right? V will become infinity in a finite time. This phenomenon is called wave breaking. for the obvious reasons. You see what the profile of the solution would look like. You start with something with a negative slope, smooth but negative slope, and then as it propagates along the characteristic, that profile gets steeper and steeper, and there's a point at which this becomes minus infinity. Solution breaks. Beyond that point, you don't have smooth solutions. Okay. Now I want to show you something that is not as well known as this one here, namely that there are other mechanisms that may forecast the breaking or the demise of smooth solutions in that case. So let me consider the following situation. I consider here initial data that are very smooth, but have compact support, are compactly supported in the interval 0, 1. Initial data like that. Now, because of the characteristics, so long as I have a smooth solution, the solution has to stay 0 along this line, and also 0 along this line, and 0 out there. Right? So the support of the solution for all t, so long as a smooth solution exists, will be confined in the interval 0, 1. Now, with that solution, assuming it exists, I associate the following functional. I associate the functional m of t is equal to integral from 0 to 1 x u of xt dx. And I compute the derivative of this with respect to t. You see, if you compute the derivative of this with respect to t, what are you going to get? This will be the integral from 0 to 1. You will get x. Here you will get derivative of u with respect to t. From the equation, this is minus derivative with respect to x of 1/2 u squared. So let me put the 1/2 out here, u squared dx. So I integrate this by parts, and I find that this is 1/2 integral from 0 to 1 of u squared of xt dx. Okay. Now, on the other hand, from this equation here, by Schwarz's inequality, you have that m squared of t is less equal than the integral of x squared from 0 to 1, which is 1/3, times the integral from 0 to 1 of u squared of xt dx. So this thing here, right, is greater or equal than 3/2 times m squared of t. Right. So this will tell you that m of t, if m of 0 is positive, if you start with initial data for which m of 0 is positive, m of t will blow up, and the time it will blow up is, so blow up for at t, let's say at t less than 2 divided by 3m of 0. That's what, if you integrate the differential, the ordinary differential inequality here, you find out that the solution blows up at this kind of time. Okay? So here we have two different mechanisms. Both of them tell us that solutions don't exist. Smooth solutions cannot exist for all times. Okay? But there are two different mechanisms. So the question is, which one prevails? Which one is the real thing? What will really happen? Will the solutions be demised because of this or because of that? And it's a simple exercise to show that wave breaking wins. In other words, wave breaking will happen before this time here. In fact, again, a simple exercise here for the young students is to show that under these assumptions, namely, I define m this way and m of 0 is positive, wave breaking will occur for t less than, I think, is 1/6 times m of 0. So this disaster is not going to happen because before it has any chance of happening, the waves will break, okay? And smooth solution will disappear. Now, why did I go through this trivial exercise here? For the following very simple reason. Let's go back now and look at a serious problem, like, for instance, the Euler equations, and ask the following, the same question. Is it true that solutions for the Euler equations also blow up in a finite time? Right? Now, this is no longer a trivial problem, right? It's a serious problem that tortured mathematicians, as you will see, actually tortured particular mathematicians very much. So let's see what happens in that case. So the first answer to that question was by using an argument very similar to the argument that I used here in order to demonstrate that the solution to Berger's equation blows up in a finite time. And this argument was put forward by Sideris many years ago, 30, 40 years ago, 30 years ago. And Sideris' argument was the following, in a simplified form, in the simplest form that I can present it. Suppose that I consider the initial value problem for Euler's equation, this thing here, with initial conditions of the following type. Rho of x0 is constant. Some positive constant, let's say rho 0, for all x. And m of x0 is some function m0 of x, which is compactly supported in the unit ball. Okay. Assume that you have a smooth solution under such initial data and define a function capital M of t, a functional M of t, like this. And then compute the derivative of this with respect to t. And after some calculation, not such a long calculation, but it's recorded in the book, so if you want to see that calculation, or if you want to do it yourself for your amusement, you find out that m of t satisfies a differential inequality like this one here. Not exactly the same, but with the same nature. M dot is greater or equal m to certain power bigger than 1, right? Which also shows that capital M of t will go to infinity in finite time if the solution exists up to that point. So this will tell you that smooth solutions for the Euler equations don't exist globally in time. Okay? All right, so this is, in the book, is just 1 or 2 pages, the proof. And if you look at the original paper by Sideris that considered more general initial conditions that I have here, it's somewhat longer, but it's a short paper, a few pages. Okay? But now the question is, in the case of Berger's equation, we found out that yes, this is, such an argument is still there, but it does not really tell us the real story, why the solution blows up. It tells us the solution will blow up, but it doesn't tell us why. So one may expect that you have, for the Euler equation, you have same phenomenon, namely wave breaking. Wave breaking meaning that some first derivative of the solution becomes infinity in finite time. Okay? So one may say, okay, if it is done in the case of Berger's equation, it will be even more pronounced in the case of the Euler equation, and therefore it will be easier to prove it for the Euler equation than for Berger's equation. The answer to that, however, is that this is not the case at all. There are two reasons why the thing is much more difficult for the case of the Euler equation than it is for the case of the Berger's equation. One reason is that here, of course, we have to deal with a system and not with a single equation, right? But this is the technical difficulty, not real difficulty, not difficulty in nature, but difficulty in that the analysis has to be more complicated, okay? The real difficulty is the following. This is a phenomenon, this is an equation that applies in several space dimensions, okay? And wave breaking, one, perhaps the naive idea is to say, all right, if waves break in one dimension, then it breaks even more in several dimensions. However, the opposite is true, because in several space dimensions, we have another phenomenon which is called dispersion. In other words, the solution starts from, let's say, a finite set like this here starts out from the ball of radius 1 and spreads out, okay, as time. And as the solution spreads out, the slopes of the waves, the amplitudes of the waves may get smaller. Yeah. And therefore, you have a competition there. On the one hand, you have the nonlinearity, which acts exactly as in the case of Berger's equation, and tries to force these fronts to break. On the other hand, you have dispersion that has exactly the opposite effect. And checking which one will prevail eventually took a very long time. It was proved only, I don't know, perhaps 5 years ago. And the proof is 100 pages long. It's in a book. The author is Christodoulou. He proves that indeed what will really happen is not this catastrophe predicted by Sideris, but something like what's happening here, wave breaking, and describes, of course, how this wave breaking will happen. And as I told you, it is 1,000 pages long, right? So I don't think that, I know of 2 or 3 people who have read it, because there is now a more...
It's not 100, it's 1,000.
1,000, yes. It's exactly 1,000. It's 997, whatever, something like that. It's 1,000, right? There is now, you know, a number of people tried very hard to simplify the proof. There's a more simplifying proof now by Kleinerman and 2 of his students. And I asked him, he said, I improved it. How many pages? That was my question. The answer is 600. So, you know.
We should put an upper bound, right?
Right.
Up to that bound,
Right. Exactly. So you can see, all right. Let's have a short break, because you must be tired, and then I will continue, okay?
Yeah, we should put this.
So now let's go back to the Cauchy problem. We have seen that you can't expect to have globally defined smooth solutions, so we have to look for weak solutions. So what is a weak solution of the Cauchy problem? So by a weak solution, I mean a function defined on this interval 0t. I mean a function u, which is in L infinity. It's an L infinity function defined on this interval 0t. Of course, takes values in Rn. And it is, well, here I should say 0t cross Rm, of course, to be precise. So it's defined